Hey everyone, my name is Chris. I'm a junior full stack developer. I work with the MERN stack, MongoDB, Express, React, node.js, and a variety of other tools. Today I'm going to be talking about Big O, not the anime, the notation. Now this video isn't going to be a full dive into data structures and algorithms, just an introduction to Big O. It is going to be the first in a series of many though, so like, follow, and subscribe. Let's dive in. The two major things that we focus on when it comes to Big O is time complexity and space complexity. How long is your code taking to run, and how many resources is it using? Big O notation is essentially the language that we use for talking about how long an algorithm takes to run. Realistically, when your code is being run in different places on different machines, the runtime is also going to be different. So Big O doesn't measure runtime in milliseconds, but in scale and efficiency, meaning that as your input increases, how much does your algorithm slow down? When comparing two different algorithms, Big O answers the question of which one is better when it comes to scale, regardless of the differences in computing power. This is probably the most common diagram you'll run across when researching Big O, and understanding it is really important to understanding Big O and the importance of time complexity. When using Big O notation, we concern ourselves with O, the number of operations, and N, the number of elements in our input. More specifically, how is the number of operations affected as N increases, or how many more operations does your algorithm have to perform? This is the basic concept of algorithmic efficiency. Now, the reason I say this diagram is really important to understanding Big O and the importance of time complexity is because the slopes it depicts for different time complexities aren't accurate to the slopes of the functions. This diagram most accurately depicts the general impact of different time complexities you can achieve, while also conveying how likely you are to achieve them for any given solution. This is why I think it's a really good tool for judging at a single glance how efficient a solution is, given its time complexity, but it does distort the overall impact of some of these time complexities which we very commonly achieve. I'm thinking O of N specifically. For contrast, I prepared a similar diagram with more accurate slopes, and here we see that a time complexity of O of N, or linear time, is really just middle of the road at best when it comes to its overall efficiency. I'm using O of N specifically because it's generally the most common time complexity we can achieve. If you've ever written a for loop that iterates over an array n number of times, then you've achieved a time complexity of O of N. And sometimes, a lot of times, O of N is the best we can do. Which is why while this diagram depicts more accurate slopes, this diagram is perhaps a much better tool when judging the overall efficiency of an algorithm. This has been a brief introduction to Big O and why it's important. Next, I'll be diving into some different time complexities with examples, and we'll go over how to determine the Big O of an algorithm. So if you liked this video, again, like, follow, and subscribe, and I hope to see you again.